In section 6.1, we study angle measure. We're going to start with some basic angles you saw in geometry, but we're going to label some information that may be a little bit different from what you know. We're going to call the ray in the angle that's pointing off to the right, directly to the right, as the initial or standard position. If I were to put this angle on a coordinate plane, this would be the ray that points off in the positive x direction. So in this angle, this is the initial ray. The way we're going to determine angle measure is going to determine on what direction we have to go from the initial ray to something called the terminal ray, and the word terminal means end. Now, in mathematics, when you go counterclockwise, this is going to be positive angle measurements, which is kind of opposite of what you think. You would want clockwise to be positive direction because that's something that you know very well. But for our purposes, positive will be the counterclockwise direction. And then if I start at an initial ray and I have to go clockwise to get to the angle, this is going to be a negative angle when we go clockwise. Now, since radians are the angle measurement most important for calculus, we'll spend most of our time with that. But that doesn't mean we won't still give you angle measurements in degrees. We've already discussed a radian. 1 radian is if you have a circle whose radius is 1, and you take that length of 1 and pull it around the curvature of the outside of the circle, that length is said to be 1 radian. And in a coordinate plane, if you go counterclockwise, let me make a nice circle here. We say that this direction here would be 0 radians. So in the counterclockwise direction, this will be pi over 2 radians, or 90 degrees. This is pi radians, or 180 degrees. 3 pi over 2 radians, or 270 degrees. And then when you've done a full circle, or 360 degrees, you end at 2 pi. To convert from degrees to radians, you multiply by pi over 180. And if you want to go the other direction and you start with radians, and you want to change radians back into degrees, you multiply by 180 over pi. So let's use these formulas real quick. In the first example, I want to convert 60 degrees to radians. So you take 60 and you multiply it by pi over 180. The best way to do it is to make it 60 pi over 180, and then you reduce this part of the fraction, and when you reduce that part in your calculator, you get 1 over 3. Remember that we don't write the 1 in front of the pi. Pi is not a variable, but it's going to work like 1. So even though you don't see the 1 in front, it's called an implied 1. So 60 degrees is the same as pi over 3 radians. To go the other direction, if you start with a measurement in radians and you want to make it degrees, you multiply by 180 over pi. Well, when you multiply those fractions together, notice the pi's cancel. And 180 divided by 6 is going to be 30 degrees. Coterminal angles are angles that lie in the same position in the standard xy coordinate plane, but have a different measurement. Let's start with this basic angle. Remember that standard position, or initial position, is the ray that points in the positive x direction. So if I go counterclockwise 45 degrees, I'll be halfway between 0 and 90. And 45 degrees in radians is pi over 4. And this is the positive angle direction. Well, what happens if I start there and I go around in a complete circle and stop in the same place I started? Well, I'm no longer at 45 degrees. When you make a complete circle, you add 360 degrees. So now you're at 405 degrees. Now, let me make that look nicer. There we go. Now, in radians, one complete circle is the same thing as adding 2 pi radians. Remember, in order to add fractions, they must have a common denominator. So I need to make these be equivalent fractions. 2 pi is the same as 8 pi over 4. Now they have a common denominator, and I find out that I'm at 9 pi over 4. What if I instead start at my 45-degree angle, and instead of continuing counterclockwise, I decide that I'm going to start here and I'm going to go clockwise, a full circle? Well, clockwise, we said, is the negative direction. So instead of adding 360 or 2 pi, instead I would subtract. So I would start with 45 degrees, and I would subtract 360. And then I would be at negative 315 degrees. Remember, the ray is in the same place on the coordinate plane. It just has a different angle measurement. And these are called coterminal angles. 45 degrees is in the same location as 405, or 9 pi over 4. It's in the same location as negative 315 degrees, or if I'm dealing in radians, instead I would subtract 2 pi. And again, same thing, I got to have a common denominator, and I would find out it's at negative 7 pi over 4. Now, this is just an example of two different angles that are coterminal with 45 degrees. There are actually an infinite number of angles coterminal with 45 degrees. I could have started at 45 degrees and gone around once, twice in a circle, in which case I would have added 720, or I would have added 4 pi, or I could have gone the other direction 3 times. I could have gone clockwise 3 times. So there's an infinite number of answers to this problem. The simplest way to find a coterminal angle is to either add or subtract 360 degrees or 2 pi radians. Find an angle with measure between 0 and 360 degrees that is coterminal with the angle of measure 1,290 degrees in standard position. All that means is that we got to 1,290 degrees by starting at 0, or a ray along the positive x-axis. Well, how am I going to find an angle that's between 0 and 360? Well, 1290 is clearly a lot bigger than 360, so wherever it is, I might need to go the other direction, i.e. in the negative direction, to find the angle that's between 0 and 360. The easiest way to do it is to just subtract 360. Now, I'm writing it here. However, you would just do this in your calculator until you got an answer that was between 0 and 360. So I subtract 360 once, I'm at 930. I'm still too big, so I'm going to do it again. Now I'm at 570. I'm still too big, so I'm going to do it again. And this is where I end up, 210 degrees. Well, now I know where this angle is. Now, the reason we do this is because it is usually easier for us to work with angles that are between 0 and 360 degrees. So if you have an angle that is much larger than 360 or much smaller than 0, you're either going to add or subtract 360 or 2 pi until you get an angle that's in our one full circle. So we found out this is 210 degrees. Well, where is 210 degrees on the xy coordinate plane? Well, if you remember that we're going to start, oops, I should change colors. Here was 0, And 210 degrees is positive, so we go in the counterclockwise direction. You are at 90, and then you're at 180. If you go another 90, you're at 270, so it must be about here, would be 210 degrees. So 210 degrees would be a terminal ray located in quadrant 3. Now let's talk about a concept we talked about in geometry, but we're going to talk about it with a trigonometric aspect. In geometry, we learned how to find the length of an arc if we knew the radius of the circle and we knew the angle between the two rays that made the arc. Now what we did in geometry was we would find out what percent of the circle that angle took up. And then you find the length around a circle, called the circumference, by doing 2 pi times the radius, or we used to say pi times diameter, but this one's more useful for us. So if, for example, I gave you a 30-degree angle, and I said the radius was 1, you would find the length of this arc by first doing 30 over 360, because remember, it's not a full circle, it's only this percent of the circle, and you would multiply that by 2 times pi times the radius. And that would tell you the length of the arc. Well, now that we know radians, we have a nicer way of doing this problem. The length of an arc S is equal to the radius times the central angle, theta, as long as theta is in radians. So now, if I go back to this problem here, a nicer way of doing the problem is to instead multiply the radius 1 times the radian equivalent of 30 degrees, which is pi over 6. And you end up with the same answer. And if you don't believe me, try it out. Now let's use this formula. Find the length of an arc of a circle with radius 10 meters that subtends a central angle of 30 degrees. Don't freak out about the word subtends. The problem is just asking you to find the length of the arc. Well, the formula for the length of an arc is this, as long as theta is in radians. Well, 30 degrees is easy, it's just pi over 6. So the arc length must be the radius times theta. And you end up finding out that it's 10 pi over 6, or 5 pi over 3 meters. Length, remember, is a linear concept, so it should be in single units, like meters, centimeters, inches, something like that. If you actually multiply this out, 5 times pi, 3.14159, divide by 3, I'm okay with that as well. In part B, we're going to do something a little different. A central angle theta in a circle of a radius 4 meters is subtended by an arc of length 6 meters. Find the measure of theta in radians. Well, this time they told me the arc length, and they told me the radius. They just didn't tell me theta. So I have to solve this problem for theta. Well, if you look back at this formula here, you just solve for theta by dividing the arc length by the radius. So 6 divided by 4 is 3/2. And the units are radians because remember, we're finding the measure of an angle. And if you tell me the answer is 1.5, I'm okay with that too. We're also going to talk about finding the area of a sector. Again, a concept we did do in geometry. But now that we know about radians, we can find the area of a sector by doing the area is equal to 1/2 times the radius squared times theta. And theta has got to be in radians. That's the kicker with these problems. A lot of times students forget when they use these formulas that theta has to be in radians. So how did we do this the old-fashioned way? Well, you had a circle, and you had this sector here, maybe I'll just use radius 1 again because that's the easiest way to do it. And then this angle was 30 degrees. And when you wanted to find the area, you knew the area of a circle was pi r squared. But we didn't want the entire area of the circle. We wanted only a portion of it. And this was the portion of the circle we wanted. So we would take 30 over 360 and multiply it by pi times the radius squared. And you ended up finding out that it was pi over 12, or maybe you did 3.14159 divided by 12 in your calculator, and that's how you found out the area. Well, now that we have another formula, we could instead do 1/2 times the radius squared times the angle in radians. Guess what? You're going to find out it's the exact same thing. The area of the sector is still pi over 12. Let's find the area of a sector of a circle with central angle 60 degrees if the radius of the circle is 3 meters. First off, if you're going to use the formula I just gave, you better change this back into radians. The reason I'm writing it very quickly, rather than going through the process of multiplying it by pi over 180, is because it is important for you to be able to know some of our special angles in radian without having to go through this process every time. It'll just make your life easier if you memorize it. So 0 is 0, 30 degrees is pi over 6, 45 degrees is pi over 4, 60 degrees is pi over 3, 90 degrees is pi over 2. It'll help you out. All right, now I'm ready to plug into the formula. The area is 1/2 times the radius squared. Don't forget to square the radius. That's the number one thing that students forget when they use this formula. Times pi over 3. Well, you get 1/2 times 9. I'm going to write it as 9 over 1 times pi over 3. How do you multiply all those fractions together? You multiply the numerators together. You multiply the denominators together. And then if you can reduce, you do. And there's the area in meters squared. Remember, area is in units squared. Suppose a point is moving along the outside of a circle. It starts here, it's going in this direction. There are two ways that you can describe the motion of this point. We have something called linear speed, and we have something called angular speed. The linear speed of the point is the rate at which the distance traveled is changing. So linear speed is the distance traveled divided by the time elapsed. We use v to represent its speed. V, remember from physics, is velocity, and it's going to equal the distance it's traveled, which is going to be the length of your arc, divided by the amount of time that it takes to get between those 2 points. The angular speed is the rate at which the central angle theta is changing. So the angular speed is the number of radians this angle changes divided by the time elapsed. Angular speed, we're going to use this Greek letter. I know, it looks like a W. This is actually the lowercase Greek omega. I know you're so excited. You're learning a foreign language in mathematics and physics. Omega is going to be our angular speed, and we just said that it's equal to the radians divided by the amount of time that it takes to traverse that angle. Let's actually use these formulas now. A boy rotates a stone in a 3-foot-long sling at a rate of 15 revolutions every 10 seconds. That means he's got this stone in a sling, and it goes around in a circle 15 times every 10 seconds. Find the angular and linear velocities of the stone. And let's just start with the angular velocity. In order to find the angular velocity, we need to know the radian angle measurement that is traversed by this 15 revolutions. Well, that means it goes around 15 times in a circle every 10 seconds. Well, 15 times in a circle in radians is 15 times 2 pi, because every circle is 1 2 pi. I shouldn't say 1 2 pi. I meant just every revolution is 2 pi radians. So 15 times 2 pi is 30 pi radians. So it goes 30 pi radians every 10 seconds. So what is its angular speed or angular velocity? Well, it's 3 pi radians every second. For the linear speed or linear velocity, I need to know the arc length that it travels. Well, the arc length is going to be the circumference of that circle. Well, remember, the circumference of a circle is 2 pi r. So it goes around 2 pi r 15 times. Oh, by the way, what's the radius? Well, the radius is that 3-foot sling. Here's my boy, and he's got this sling, and he's rotating it around in a circle. So that's going to be my radius. So the circumference for one revolution is going to be 2 times pi times 3, which is 6 pi. But he does this 15 times, so now I have to multiply this by 15, and 15 times 6 pi is going to be 90 pi radians, not radians, sorry, this one's feet, because that's the arc length. And he can do this 90 pi feet every 10 seconds. So his linear speed is going to be 9 pi feet per second. Notice that the angular speed doesn't depend on the radius, but only on the angle. However, if we know the angular speed, omega, and the radius r, we can find the linear speed like this. Remember that we said s a moment ago was r times theta. Well, if I take this and instead rewrite it like this, isn't theta over t just omega? So the relationship is that the linear velocity is also the radius times the angular speed. A woman is riding a bicycle whose wheels are 26 inches in diameter. If the wheels rotate at 125 revolutions per minute, RPMs, find the speed at which she is traveling in miles per hour. Well, first of all, notice that at the end of the problem we want to be in miles per hour. And we're starting with a problem that has inches and minutes in it. So we're going to have to make a change at the end of the problem. We're going to have to use something called dimensional analysis, which you've done quite a bit of in chemistry. Well, let's start with the easy part of the problem, which is that the velocity is the radius. Well, first of all, they told me the diameter was 26 inches, so the radius is going to be 13 inches. And the angular velocity is going to be the angle over the amount of time. Well, I know these wheels are rotating at 125 revolutions per minute. Well, I need to know the angle, so you have to multiply 125 times, when you go around in a circle, you go 2 pi radians, and you're doing this once every minute. So you find out it's actually 250 pi radians per minute. So I know omega. So V must equal 13 times 250 pi. Well, remember that the 13 is in inches, and the 250 pi is in radians per minute. So we're going to find out that this is 13 times 250 pi, or approximately 10,210.2 inches per minute. Well, inches per minute is lovely, but we don't want our final answer in inches per minute. We want it in miles per hour. So let's do the fun part of the problem. The fun part of the problem is changing the units. 210.2, and this is inches in 1 minute. And in order to change this into miles per hour, you need to remember that there are, let's start with the easy part, there are 5,280 feet in 1 mile. But we're in inches, so you have to take that 5,280 and multiply it by 12. So you end up with 63,360 inches are in 1 mile. So I'm going to first multiply that fraction by 1 mile over 63,360 inches. And then to change minutes into hours, I know that 60 minutes is 1 hour. So the minutes cancel, the inches cancel. You multiply it all together, and you end up finding out that it's about 9.7 miles per hour, which is pretty slow.